Now let us see what is meant by clock gating. So generally this clock gating comes into the picture whenever you want to disable the clock for some portions of the block within your design, so that it helps in power saving. That is, dynamic power consumption can be reduced. So coming to clock gating technique has become very popular since mid 1990s to reduce power consumption. Power in a circuit is consumed when a flip-flop or register in the design switches state due to clock trigger. So whenever clock is getting triggered, it leads to on and off. Suppose if you take an example of an CMOS inverter, let me draw the diagram of CMOS inverter which contains one PMOS and one NMOS. Here top will be VDD and here bottom will be ground. Here this portion will be input, this will be the output. So generally some capacitor will be present here. So whenever you are applying inputs, that is whenever input is equal to 0, this will be on and this will be off. So whenever it is on, it acts as short circuit. This leads to charging. So capacitor will get charging. Similarly, when you are applying 1 at the input, it will get discharged. So charging will happen from PMOS and discharging will happen through NMOS. So this is nothing but switching activity. Whenever input is getting switching, this leads to charging and discharging of capacitor. So because of this leads to some dynamic power consumption. So however, in a design portion of the logic may not be getting used at certain times. So by using this particular clock gating concept, what we do is, if some part of the design does not require clock, so generally in order to switch it off, we'll make use of this particular concept. So during that stage, disabling clock to those portions of the design reduces the switching power. This is achieved by having enabling logic before the clock, and such a clock is called as a gated clock. So generally it will be done by using some AND gate which contains some clock followed by enable, so that we get output as some gated clock. So whenever it is not net, so depending upon the enable pin, clock will be given or else clock will be disabled. So generally enable pin can be either 0 or 1. So if you see the figure of a gated clock, it will be something like this. So this is a flop and here I am doing gated clock by using an AND gate. So this clock is getting controlled by the enable pin. So here if you see figure 6.3 shows the example of a gated clock. We can also use clock gating to obtain divided clock with waveforms similar to those of figure 6.1. So this concept we have already seen, like 2-bit triple counter. Like initially at LSB we are getting divide by 2 and here I am getting divide by 4. So let me write here, I will get divide by 2 and again here divide by 2. So overall it will become divide by 4. So the same concept can be achieved by using this gated clock. So the concept of clock gating can be extended to create clock pulses. So let us see the figure 6.4 where the clock is gated via a chain of odd number of inverters. So here this is the same diagram. Here for the sake of delay you can use either inverters or buffers. So here we are using 3 inverters which are connected back to back. Depending on the delay on the chain of inverters, a pulse will be generated. This method is used to improve performance and reduce power as well. It is important to ensure that clock gating is typically done with only one clock. Now let us see what is happening with this. So if you see the figure, a gated clock to generate pulses. So we need to apply some clock and the delayed version will get applied to the another pin of this particular AND gate, and by using that we'll get the pulse. So simply for one AND gate I am applying one input, followed by here I am giving some delay and I am applying another input, so that I am getting output which is nothing but a pulse. So this is the clock that I am applying and this is the delayed version, like it is getting delayed by using 3 inverters and I am getting some pulse. So simply you can use a function of an AND gate for an AND gate which contains 2 inputs and 1 output. So 0 0 0 1 1 0 and 1 1. So this is the truth table. So you can check here, whenever this portion is 0 and this is 1, 0 into 1 will be 0 and here it is 1, here it is 1. So 1 into 1 is 1, so it is going high. Next here it is 1 and 0, 1 into 0 will be 0. So by using this you can get the pulse which is shown here. Now let us see how to write the constraints. So generally this portion is common. I am taking a time period of 10 nanosecond. So we have to write create generated clock command for this particular pulse. So create generated clock hyphen name, this is the name, pulse, hyphen source, from where it is coming from, this is coming from the clock port. So get port CLK. Now we are writing it by means of an edges. So here check this pulse with respect to CLK. So here I am getting one rising edge, here one falling edge, here one rising edge. This rising edge number is 1. This falling edge number here as nothing is there, so obviously here also it will be 1. And this rising edge number is 3. So simply edges will be 1 1 3. So that's what I have written here, 1 1 3 at the edges. Next, get pins AN1 is nothing but instance name for that particular AND gate, and Z is the pin name of AND gate. So here also same concept is applicable. This is A, this is B, this is Z. So 2 inputs and 1 output. And here AN1 is nothing but the instance name. So that's why I'm writing here as get pins, instance name followed by the pin name. You can ignore the slash line.